So we have a p-series. P-series just looks like something in the form of this. So for example, um, if I have the infinite sum from 1 to infinity, right, of let's say 1 divided by n to the second power. Now, when you're writing out p-series, you just want to focus on the exponent. So if your exponent in this case is greater than 1, it's going to converge. And if the exponent is less than or equal to 1, then it's going to diverge. So in this case, this sum is actually going to converge because my exponent is greater than 1. The exponent is big enough that, as n increases, it's actually going to add towards a specific value. Meanwhile, let's say if n was, I don't even know, n to the, n to the, let's say, negative second, for example. All right, so p in this case is less than or equal to 1, right? P of this in this case is negative, and we can rewrite this as essentially n to the second power, right? Because n to the negative second power on the denominator, you just flip it up to the numerator. So all of this is going to be equal to n to the second power. And of course, as you see, as n increases, well, as my value for n increases, well, it's just going to keep on getting bigger and bigger, right? As I go from the first term to my second term, so when n is equal to 1, I have 1 squared, n is equal to 2, I have 2 squared, which is 4. So as I keep adding all of these terms up all the way right over here, well, my value is just going to get bigger and bigger. So if I try to sum all of this up, it's just going to keep on getting bigger and bigger, so it's going to diverge. This idea can sort of be applied to other sums. So for example, let's say if I have, oh my god, it's pretty bad. Let's say if I have, this is from n is equal to 1 to infinity. And let's say if I have 5 divided by n squared. Then what I can do now is I can just move the 5 to the front. So I just take this 5, I move it to the front. And then now I have this p series here. And depending on if it converges and diverges, then I can figure all of that out. So that's kind of the first thing to look out for. Sometimes you're able to sort of simplify this so that you remove sort of the numerator and then your result is a p-series. If we have like a sum like this, as n approaches infinity, the dominant terms are going to be this term, right? This term is going to dominate over the 5. And this n to the 2.5 is going to dominate over the 7, right? If we're summing all the way to infinity, at this point, these two terms really do not matter. So the terms that really do matter is these terms right over here. So what I can do is just get rid of this. These are just the two terms I really need to focus on. Now I can simplify this, right? N to the second power divided by n to the 2.5, that's going to be equal to n to the 0.5 using my exponent properties, right, on the denominator. And what I can do now is I'm going to use the same strategy as before. I'm going to take this 3, I move it to the front, and all of a sudden, boom, I have this p-series. And because p is less than or equal to 1, it is going to diverge. So you see, this is a pretty powerful tool whenever you're dealing with, polynomial stuff like this. Well, n to the 2.5 on the bottom isn't really a polynomial, but a lot of times you might be dealing with polynomials, and so you're able to simplify things by looking at the most powerful terms, and you're able to simplify. If we have something like 5n plus 4 divided by n to the third power, just focus on the biggest terms, 5n and n to the third power. N divided by n to the third power is just going to lead you to an n to the second power on the denominator. Move this 5 up to the front, put 1 here, and boom, you have p-series, n to the second power. Well, that's 2 is greater than 1, right? So this is just going to converge because the exponent is big enough to kind of balance everything out. And yeah, there we go. All right, now we have here, this one. What do? We just focus on the terms that actually matter. So in this case, this n to the fifth power is going to outweigh the 3n in my numerator. So I don't really have to focus on the 3n. And for my n to the fourth and this plus ln of n to the seventh, when you have a polynomial, polynomials always grow faster than logarithmic functions if you're dealing with infinity, right? As n approaches very, very large number, polynomials always outgrow logarithmic. So we can kind of just ignore this logarithmic here, okay? It's kind of like the same thing you do with limits, like the shortcut for it, right? Just focus on the biggest terms. The square root of n to the fifth power, the square root of something is the same thing as raising that thing to the 1/2 power, right? So it's the same thing as raising this to the 1/2 power, and 5 times 1/2 gives me 5 over 2. If we subtract these, I'm just going to get 1 over. So originally I had n to the 5 over 2nd power, and I'm subtracting this by n to the 4th power, right? So 5 over 2nd minus 4, that's going to be equal to 1.5. Because 1.5 now is greater than 1, this is going to converge. So there we go. Whenever you're dealing with like limits or something, you want a really easy like shortcut way. Just remember that polynomials always grow faster than logarithmic. So if I have a polynomial, let's say n to the c power, right, that's always going to grow faster than, let's say, log of n. Exponentials, so in this case c to the n, is going to grow faster than polynomials. Factorials are always going to grow faster than exponentials. And finally, power towers are always going to grow faster than factorials. So let me give you an example. So if I have, let's say, log of n, that's actually going to grow slower than, let's say, n to the 2nd power. However, 2 to the n power is going to grow faster than n to the 2nd power. But then n factorial is going to grow faster than all of these. And finally, n to the n power is going to grow faster than all of these. Okay.